What's good, guys? Welcome back to another video. Today we're going to be going over something called related rates. Essentially, what a related rate is a calculus idea where we are correlating multiple rates of measurement together. Examples of this include distance over time, radius over time, volume over time. There's usually a time element that you're kind of getting here, but the main thing is not only are we taking the instantaneous rate of change, we're taking the instantaneous rate of change in respect to another idea in um, in relation to another rate. So without further ado, let's get right to it. All right. So my first question here is this. A company's revenue from selling X units of an item is given as R equals 1200 x minus x squared. If sales are increasing at a rate of 35 units per day, which I'm going to write this over here for a second, I'll explain it in a second, but in this case, dx dt is equal to 35. How rapidly is revenue increasing in dollars per day when 320 units have been sold? X equals 320. So, what is this? Dx dt is something called implicit differentiation. What essentially it is we are taking the derivative of x with respect to something else. So not only are we trying to find the instantaneous rate of change of x in this case, we're trying to find the instantaneous rate of change of x when also there's a rate of change in t as well. It's a combination, which gives us this idea. So how do I solve one of these? Well, what I'm going to do is I'm going to take the derivative of this thing, which is going to be equal to, well, this is going to equal 1200 minus 2x, and then I have to use the chain rule dx dt. Now, why am I putting dx dt here? Well, the reason why is exactly what I said, chain rule. But you're sitting here, you're being like, well, everything is in terms of x, so why are we taking chain rule? It's because of this implicit differentiation idea. What it means is there's technically a mini t value in here. X is not x anymore. In fact, every time you see x, it's actually x of t. X is now a function. It is a function of t. So when I take the derivative of x, it's going to have chain rule where I also have to take the derivative of this t value, but t is not included here. So we, as math people, show that by putting dx dt, being like, hey, we can't see it. We have to acknowledge the fact that this is chain rule. There is some t value here since t is getting involved, and that's it getting involved there, right? It's almost like that little brother situation where, or like a kid situation where you just give them a steering wheel to pretend like they're driving, but in reality they're not pressing the gas or steering the wheel. It's like, here, I know that you're trying to get involved. I don't see you. This is us getting you involved. So then from here, all we do is we just plug in, just like any normal equation. In this case here, I get 1200 minus 2. Well, my x value is 320. 320 times, well, dx dt was provided to us, 35. And essentially all this, comes out to 19,600, giving us our final answer. On to the next one. All right, second question is this. A street light is at the top of a 12-foot tall pole. Anytime we're trying to have it's gonna look like it creates a shape, like you kind of have to think about it, it's best to draw it. So in this case, I have a 12-foot tall pole. Let me just draw that. 12-foot tall pole. All right. A woman 6 feet tall walks away from the pole with a speed of 8 feet per second. So 6 foot tall woman, some distance away, walking at the rate of dx dt equaling 8 feet per second. So 8 here. Now the fact that I am deriving this as x, I'm going to call this x right here. because she's walking away. This is the distance she's walking away. Okay, and then I can delete this part too. All right. How fast is the tip of her shadow moving when she's 35 feet from the base of the pole? Okay. So in other words, her shadow is this y value here. And how fast is essentially we're moving from the base when we are 35 feet away. So x is equal to 35. Right. Well, notice what I'm basically solving for here is just the bottom. Because it's what it says here is how fast is the tip of her shadow moving away when she is 35 feet away from the base. So I'm going from here, right? It's not like I'm having to try to find the hypotenuse here or anything like that. I'm just going from here to here. Okay, well, what am I noticing? Well, what I'm noticing is I have a little mini triangle inscribed in the big triangle. What is that set up for? Similar triangles. So what I'm going to do here is I'm going to set up their proportion. 12 over x plus y, forgot, is equal to 6 over y. Well, from here, what I'm going to do is I'm essentially going to solve. The reason why is because all I have to do is just add x plus y. I just got to figure out this whole thing. But when it comes to solving equations, I always need it in one variable. If I have it in multiple variables, things get kind of weird. So I'm going to try to set x to y. So cross multiply. I get 12y equals 6x plus 6y. Well, from here, I can subtract 6y to both sides. Get 6y equals 6x. Divide everything by 6 and get x is equal to y. Well, in that case, like I just said, the total distance, I'm just going to put t here, is equal to, well, x plus x in this case, it's x plus y. But I know that x is equal to y, so x plus x, which is 2x. And what I do is I just have to take the derivative of this thing. There. Now, if I take the derivative of 2x normally, it would just be 2. But remember, chain rule, because there's that little mini t that's there. So this is equal to 2 dx dt. And then since I was provided that dx dt is equal to 8, I get 16 feet per second, I believe. Right? Feet. Yep, 16 feet per second. And there you go. All right, on to the next one. All right, next one here. We got a spherical snowball melting at a rate of 8 centimeters per minute. Well, I'm hearing sphere. Sphere is three-dimensional. So I'm automatically thinking volume. And it's melting at a rate of 8 centimeters cubed per minute. Centimeters cubed means we're dealing with volume. So dV dt is equal to -8. And why? Well, because it's melting. In other words, it's decreasing at -8 in this case. And the reason why I chose dV dt again is because it's volume, but that is the rate at which it is. So it's not just volume, it's the rate. Now, how rapidly is the radius decreasing when the snowball's volume is 4,500 pi centimeters cubed? So volume is equal to 4,500 pi. All right. Well, now what do I got to do? Well, it's looking like they want us to use volume, so we're going to use volume here. Well, the volume formula is equal to 4/3 pi times the radius cubed, right? Well, anytime we're dealing with a related rates question, I got to kind of think about what I'm solving for. I'm solving for how rapidly the radius is decreasing. Okay, so that's rate of change in terms of radius. Again, with respect to time, because it's how fast. So I'm trying to solve for dr dt. That's what I'm solving for. Well, I need to be able to have every other variable in the equation other than dr dt in order to solve it. Because if not, I'm going to have multiple unknown variables. So that means I need to find r. Okay, well, how am I going to do that? Well, I'm given the volume. So why don't I just plug that in and solve for r? So I got 4,500 pi is equal to 4/3 pi r cubed. Well, I need to get the 3/4 to the other side, or the 4/3 to the other side, so I'm going to multiply by 3/4. The reason why is because I'm dividing by 4/3, same thing as multiplying by the reciprocal. So this is, in other words, 3 times 4,500 pi over 4. I'm going to divide by pi. Divided by pi is equal to r cubed. This all ends up equaling 3,375, which is equal to r cubed. I'm going to take the cube root of both sides, and I get r is equal to 15. All right, so now I have all of the variables that I need. So what do I do now? Well, it's not asking me for the radius, it's asking me for the radius with respect to time, the amount it's decreasing. So in other words, what I'm going to have to do here is I'm going to have to differentiate. So I'm going to differentiate the whole thing, right? Essentially, this is what I'm going to be doing, taking the derivative of the whole thing. And that gives me dv dt is equal to, well, the 3 goes out in front, so 4 pi r squared. And then again, remember, chain rule, there's a little mini t in there. So dr dt, well, dv dt is equal to -8 is equal to 4 pi times 15 squared dr dt. And then from here, it's just solving, right? I'm going to divide everything by 4 pi times 15 squared. That's going to give me -8 over 900 pi is equal to dr dt. So in other words, the radius is decreasing at a rate of -8 over 900 pi units. I think it was per second, something like that. Essentially, that's how you do it. Let's keep it moving. All right, we're halfway through these. So now the next one, the altitude of a triangle is increasing at a rate of 2 centimeters per minute. So altitude is another word for height. So I got dh dt is equal to 2. While the area of the triangle is increasing at a rate of 1 square centimeters per minute. So dA dt in this case is equal to 1. At what rate is the base of the triangle changing when the altitude is 8 centimeters and the area is 83 centimeters? So height is 8, area equals 83. Okay, well, what am I trying to solve for? It says, at what rate is the base of the triangle changing? So I'm trying to solve actually for dB dt. This is what I'm solving for here. Well, I'm given a lot. So clearly area is involved, right? I'm given the derivative of the area with respect to time, and I'm also given the area itself. Well, what is the area formula for a triangle? A equals 1/2 base times height. Well, what did I say last time when it comes to related rates? I need to have every single variable other than the one that we're trying to find. All I'm trying to find is dB dt, which means what am I missing? B. So I have to solve for that first before I do anything else. So in this case, I'm going to plug stuff in. 83 for A, so 83 is equal to 1/2 B times 8. Well, 1/2 times 8 is 4. So this is all going to end up equaling 83 divided by 4. And then 83 divided by 4, well, 4 goes into 8 2 times. 4 does not go into 3, so 0, with a remainder of 3/4, also known as 20.75. All right, well, that's my base. My base is 20.75. Cool. Well, now I have to solve for dB dt. So again, I come back to area equals 1/2 base times height, and I'm going to take the whole derivative of the whole thing with respect to t. That gives me dA dt equals 1/2. And notice this is base times height, so that's product rule. So b times dH dt plus h times dB dt. Well, now I'm going to plug everything in, so I get 1 equals 1/2. B in this case is 20.75. H is 8, but it's going to be divided by 2 there. So, well, let me just plug everything in, and then we can do that afterwards. Times 8 plus H. Oh, dH dt. dH dt is 2. I lied, so this is going to be 2. And then this one here is going to be 8 times dB dt. And again, I'm distributing everything here. So this 1/2 is going to go with this 2. That's going to turn into 1. This is going to turn into 4 here. So in other words, let me erase this over here. I'm going to get 1 is equal to 20.75 plus 4 dB dt. I'm going to subtract 20.75 from both sides. Get negative 19.75 equals 4 dB dt. Divide everything by 4. And that's just going to be my final answer there. dB dt is equal to 19.75 divided by 4. And I'll just leave it like that. All right, next one here. An inner city revitalization zone is a rectangle that is twice as long as it is wide. Okay, so in this case here, L is equal to 2W. All right, the width of the region is growing at a rate of 31 meters per year. Okay, so the width is growing at a rate of 31 meters per year. So this is 31. All right. When the region is 250 meters wide, W is equal to 250. How fast is the area changing at a point in time? Right, so now we're dealing with area. Well, what is the area formula? Area is equal to, well, length times width. But I'm given length. Length is 2W. So in other words, 2W times W. Well, that's the same thing as just 2W squared. Now in this case, I'm already provided W, and I know that I'm taking the derivative of the area, so I don't need to solve for anything here. I don't need to solve for any other variables. I can just differentiate. So differentiate this thing with respect to time. I get dA dt is equal to 4W dW dt. And then I just plug everything in. 4 times 250 is 1,000 times, 1,000 times dW dt is 31. So in other words, dA dt equals 31,000. All right, on to the last one. All right, the last one reads like this. Water is being pumped into an inverted conical tank at a rate of 12.1 cubic meters. Okay, again, I'm sitting here reading and I'm seeing cubic. That means volume. So in other words, dV dt is equal to 12.1. And it's positive because it's being pumped into this conical shaped thingy. I don't know. The tank has a height of 8 meters. Okay, so height equals 8. and a diameter at the top. And the diameter at the top is 7 meters. Okay, well, automatically, I'm given volume. So I know that we're going to be using the volume formula for a cone, which is 1/3 pi r squared h. Notice it's in radius terms. So I'm not even going to write the diameter. I don't care. I'm just going to write it as the radius, 3.5. Okay, find the rate at which the water level is rising when the height of the water is 5. Whoa, okay. So this is height. I'm going to put a subscript here, height total, because this is the total height. The height water level, so HW here, is 5. Okay, this is one of those ones that's probably better to draw. So I'm going to try my best to draw here. I'm given a cone, and I know that the height of this thing is 8. And I know that from here to here is 3.5. But it wants me to find the height of this when the water is at 5, right here. So how would I solve this? Well, I need to solve this thing in relation to height. I'm given the height and I'm given the radius here. Notice that if I draw a line directly through here, I'm creating this kind of like triangle shape here, and then there's a mini triangle. So in other words, I can use, again, similar triangles. I can do the radius of the total over the height of the total is equal to the radius of the water over the height of the water. In other words, I'm setting up this similar triangle idea. Well, remember, in order for me to solve an equation, I need everything to be plugged in for other than what I'm solving for. I'm solving for dH/dt. I'm given height. I'm given the radius of the whole thing. The only thing that I'm not given is the radius of the water level right here. Well, do I need it in this case? No. The reason why is because what I can do is I can basically use this similar triangle idea to rewrite radius in terms of height. Well, how do I do that? Well, I'm going to multiply both sides times the height of the water. And I'm going to get the radius of the water is equal to, well, the radius of the total is equal to 3.5 over 8 height of water. Let me just put that there. So now, when I plug it back into this equation, everything's going to be in terms of height. And since I'm already given the height of the water, I'm good, right? I don't have to really worry about it anymore. So what I'm going to do now is I'm going to rewrite this equation. So equals 1/3 pi times, well, in this case, I don't really like the decimals, so I'm going to multiply the top and bottom by 2. Again, I'm just basically creating a common fraction, right? Just a more convenient fraction in this case. 7 over 16 squared height times height. All right. Well, now what I'm going to do here is I'm going to simplify. I'm going to rewrite all of this. This is all going to end up equaling 49 pi over 768 h cubed v. All right. So now we're set up. The reason why we're set up is because I know the height, okay? I know that I'm going to take the derivative of this thing, and I know the derivative of the volume with respect to time. So we're all good, right? We're all set up. It's perfect. So I'm going to take the derivative of this whole entire thing. That's going to give me dv dt is equal to, in this case, 49 over, well, I'm going to put 3 in front. That's going to reduce the fraction. 3 goes into 7 2 times with 1 remaining. 3 goes into 16 5 times with 1 remaining. And 3 goes into 18 6 times. Pi. And then h squared dh dt. And again, in this case, I am solving for dH dt here. So I'm going to divide this whole thing by all that nonsense right there which is going to give me 12.1 over, well, anytime I divide by a fraction, it's the same thing as multiplying by the reciprocal. So actually, I'm going to multiply by 256. And then 49 goes to the bottom. So does the pi. And h, well, it's 5, which is going to be 25. It's also going to go to the bottom because it's right here. So when I'm dividing, this part actually goes to the bottom, which is equal to dh dt. And that means that dh dt equals 3097.6 all over 1225 pi. And I'll leave it in those terms to give us the final answer of the day. All right. Thank you guys for watching. If you want me to walk through some questions just like this for you, feel free to drop them down in the comments. If you want some one-on-one tutoring, always head on over to MindLeap Tutor. But until then, I'll see y'all next time. Take care. Peace out.